Hello, Physics 1 students. Today we're going to be talking about measurement uncertainty. Now, this pre-lab lecture is going to be considerably longer than other pre-lab lectures. The reason for that is because in the past, I've always had students come in with all different levels of comprehension with regards to measurement and uncertainty. Now, this is the lab section, so we're going to be recording a lot of measurements and recording a lot of uncertainties associated with said measurements. And it's really important that right in the beginning, everyone is on the same page with regards to how to properly measure things and how to properly record the uncertainties associated with those measurements. So, without further ado, let's get started. So the first thing that we're going to discuss is how you report your measurement and uncertainty in standard form. So the most common way of doing this is you write your measurement, followed by the plus or minus sign, the absolute uncertainty, then the units. Okay, so a couple examples. So for a digital balance and an analog ruler, so if you have a digital balance and you take an item and you place it on the balance and the balance reads 37.5 grams, you would record that as your measurement. Then the plus or minus sign, followed by the absolute uncertainty of that balance, and then your unit. Okay? Now, if you have a ruler and you measure the length of some item, and the length of the item turns out to be 127 millimeters, that would be your measurement. Then the plus or minus sign, then you would record what your absolute uncertainty is for your ruler, which in this case we're saying is 1 millimeter, and then your unit. Okay? Now you may be wondering right now, is there a difference between how you find the absolute uncertainty for a digital device versus an analog device? And the answer is yes, and we are going to go over it shortly. There's one other thing that I wanted to mention before we move on, though, and that's that people use error and uncertainty interchangeably. There are slight differences in the nuance of meaning, but 9 times out of 10, it's totally fine to use error and uncertainty interchangeably. Uncertainty specifically refers to the resolution or precision of your measuring device, whereas error may refer to the difference between a standard or theoretical measurement, such as gravity being 9.81 meters per second squared, and an experimental measurement that you find from conducting in the lab that might be slightly different than that theoretical measurement. So there are 3 main types of uncertainties that we're going to discuss in this lab. Those are absolute uncertainty, relative or fractional uncertainty, and percent uncertainty. We're going to start with the first one, which is probably the simplest as well, and that is absolute uncertainty. So as I mentioned before, there are 2 types of devices that you can have to record your measurements. These 2 types of devices are analog devices and digital devices. We're going to start with talking about how you'd find the absolute uncertainty for an analog device. Okay? Now, an analog device is a measuring device that has lines on it. Okay? So that could be a ruler, a graduated cylinder, a beaker, etc. Okay? Analog devices have lines. So the way that you would find the absolute uncertainty for an analog device is you would take the smallest increment on that device and you would multiply it by 1/2. Okay? So down here we have the metric side of a ruler, okay? And you'll just have to take my word for it. Each of these little lines, which is the smallest increment on our measuring device, there are 10 of these lines in between each centimeter. Okay? So that means each one of these lines represents 1 millimeter. So if we wanted to calculate what the absolute uncertainty is for this ruler, it would be 1/2 of a millimeter. Okay? Now you can see here that's not exactly what we're asking for, right? We're asking how long is this black box in millimeters with uncertainty. So we want to put it in the standard format of measurement uncertainty format. Okay? So we can see by looking at this black box here that it comes out about 3 notches after the 4. So that means that it's about 43 millimeters long. And as we talked about before, the uncertainty is a 1/2 millimeter. So we find that the answer to the question for example 1 is 43 plus or minus 1/2 millimeter. Now we are in America after all, And so we use the imperial system. So I would feel remiss if I didn't at least do one example in inches. So what is the absolute uncertainty of this measuring tape in inches? So we can see between each inch that's subdivided into a half, a quarter, an eighth, right? So the smallest increment on this measuring device is an eighth of an inch. Well, we know that in order to find the absolute uncertainty of an analog device, we need to multiply that by a half, which means the absolute uncertainty is 1/16 of an inch. All right, so now let's get into digital devices, okay, and how we find the absolute uncertainty for digital devices. So to find the absolute uncertainty of a digital device, you don't have to do any calculation at all. All you need to do is look at the device and see what the precision of the device is, and the smallest increment of precision is your absolute uncertainty. That means for this balance, it would be 0.01 grams, right? Because it goes out to 100th of a gram, right? So the smallest increment on this measuring device would be 100th of a gram. So that is the absolute uncertainty of the balance. All right, now let's start getting into how you propagate absolute uncertainty. Now, the most important thing to note about propagating uncertainty is that you never, ever subtract it. Uncertainty only ever compounds. It never goes away. Okay, so say we have this example here where we're trying to figure out what the mass of some sample is, and the way that we do it is we measure what some vessel, say we have a beaker, so we take our beaker and we place some sample in it and we weigh it, then we remove all the sample from the beaker, and then we weigh that empty beaker, and then we difference those two mass values in order to figure out what the mass of just the sample is, okay? That means that this first mass measurement with the vessel and the sample has an uncertainty of 0.01 grams associated with it, and this mass of the empty vessel also has an uncertainty of 0.01 grams associated with it. Now, just because we're subtracting these two mass values does not mean that we subtract the uncertainties. They don't cancel out. They don't go away. They only compound. We are adding up the two uncertainties associated with them, which means that the mass of the sample that we get at the end is going to have an uncertainty of 0.02 grams associated with it. So you can pretty much see everything that I was just saying on the previous slide. The uncertainty associated with the mass of the sample is 0.02 grams, and that's because we never subtract uncertainties from one another, right? Just like I said on the previous slide, the mass of the vessel in the sample has an uncertainty of 0.01 grams. The mass of the empty vessel also has an uncertainty of 0.01 grams. That means that when we add up these uncertainties, because they never go away, they only compound, we get 0.02 grams is the absolute uncertainty of the mass of the sample. All right, moving on to relative or fractional uncertainty. Typically, we're going to refer to it as relative uncertainty in here, but sometimes in other textbooks you might see it referred to as fractional. It's exactly the same thing, but I choose to refer to it as relative. All right, so now we're going to discuss relative uncertainty. Now, relative uncertainty is really handy when you have two quantities that have different units, okay? So before, when we were doing the error propagation for absolute uncertainty, all of our units were the same, right? With our example with the balance, we had grams, grams going to grams, right? But say, for example, in the lab today, you're going to be calculating density, right? So that means you're going to have a mass measurement and you're going to have a volume measurement. Those do not have the same units. So you want to use either relative uncertainty or percent uncertainty, both of which create unitless quantities in order to propagate the error. Okay, so the way that you find relative uncertainty, if you're looking at your measurements in standard form, so that means measurement plus or minus your absolute uncertainty, the way that you would find relative uncertainty would be to divide the absolute uncertainty by the measurement. So an example would be, what is the relative uncertainty of a nightstand with a length of 73.2 centimeters if you are using a ruler that measures millimeters? So the first thing that I'm going to do is I'm going to find my absolute uncertainty. Okay, now as the example mentioned, I have a ruler that measures millimeters, so the smallest increment on my measuring device is 1 millimeter. This is an analog device, so the way that I find my absolute uncertainty is I multiply by 1/2. So 1/2 times 1 millimeter is equal to a 1/2 a millimeter, and that is my absolute uncertainty. The only thing left to do is to calculate the relative uncertainty, and the way that we do that is we divide the absolute uncertainty by the measurement. Okay, as we talked about in step 1, the absolute uncertainty is 0.5 millimeters. The measurement is in millimeters is 732 millimeters. Yes, I know that in the prompt it gave it to us in centimeters, but that's going to happen to you a lot where you're going to have to perform these conversions to make sure that everything is in the same unit. And so that's what I did here, because we want to make sure that the units are canceling and that we end up with a truly unitless quantity that is correct at the end. Okay? So when you divide 0.5 by 732, you get 0.0006836, or more simply, you get 0.0007. If your uncertainty precision is smaller than the precision of your measuring device, so if it exceeds the number of significant figures, you want to round to 1 decimal place. This is a really common practice, and you can even do that if this isn't the case. It's a very common practice to just round the uncertainty off to 1 significant digit. One other thing that I wanted to mention is you may be wondering, how do I choose for a problem like this, whether I should choose millimeters or centimeters? And the way that you would choose is you would look at what your answer is at the end. Typically, relative uncertainty is going to be an intermediary step where you're taking 2 different quantities that have 2 different units, and you're figuring out what the relative uncertainties are, you're adding them up, and then you're going to convert back to a final different unit at the end. And so you'll want to look at what that unit is, okay? So to reference the lab that you're going to be doing this week, that would be for finding the density, you would have a mass in grams, and then you would have a volume in milliliters, and then at the end, you would have grams per milliliter, for example. Okay, so if you were trying to figure out what the relative uncertainty is for your mass measurement, you would want to have it in grams if your final unit is going to be grams per milliliter. Okay. If, however, like we're going to have in the lab, you wanted to have your units be kilograms per meters cubed at the end, then you would want to make sure that the gram measurement that you take off of the balance is converted to kilograms. Okay? It all depends on what final unit you're trying to have at the end. That'll determine what unit you should choose in order to cancel properly for the relative uncertainty. So the purpose of these next couple relative uncertainty examples is to show you what effect your measurement can have on your relative uncertainty. Okay? So over here we have a standard 400 milliliter beaker, and it has a measurement increment of 25 milliliters. Okay, so that's the smallest increment on our measuring device. So the first question is, what is the relative uncertainty of 100 milliliters measured in this beaker? Okay, so we take some substance, maybe water, we fill it up to the 100 milliliters line, and we want to know what is the relative uncertainty. Okay? So the first thing that we want to do is we want to find the absolute uncertainty of the beaker. Now, since this is an analog device, we need to take the smallest increment of that measuring device and multiply it by 1/2. So 1/2 times 25 milliliters, that gives us 12.5 milliliters, and that is our absolute uncertainty. The next thing that we want to do is we want to calculate our relative uncertainty. So we take our absolute uncertainty, which is 12.5 milliliters, and we divide it by our measurement, which is 100 milliliters, and we get 0.125. That is our relative uncertainty. Now you can see it's unitless because milliliters cancels with milliliters, and so this is our answer. Now let's say that we want to find the relative uncertainty of 300 milliliters measured in this same beaker. It's still the same beaker, so the absolute uncertainty doesn't change. It's still 12.5 milliliters. However, our measurement is now 300 milliliters, right? We're measuring 300 milliliters of water now. So we divide 12.5 by 300 and we get 0.042. Okay, so the reason that I mention this is because we can see that these relative uncertainties are different, right? This one is considerably smaller than this one. So the reason that I mention this is because we want to minimize our uncertainty, right? We want to be pretty exact about our measurements. And so it's important to make sure that we're using the appropriate device. So if we were measuring 100 milliliters, we might have wanted to take a graduated cylinder that only measures 100 milliliters and has a much smaller increment, right? Because that would have produced a much smaller relative uncertainty. And we're hoping to minimize our uncertainty with our measurements. Whereas this device here is much more appropriate for measuring the 300 milliliters, and that's reflected in the fact that we have a relatively small uncertainty, right? So keep that in mind. If you're doing the lab in person, you're probably going to want to fill your measuring device up to that top line in order to minimize your uncertainty. All right, so now we're going to switch gears a little bit and we're going to talk about absolute uncertainty and error propagation. Okay, so we're moving away from relative uncertainty for a minute and we're going back to absolute uncertainty. Okay, so absolute uncertainty is going to be your simple addition and subtraction problems, and this can be of multiple measurements or just a couple, but they're going to have the same units. An example would be perimeter. Okay, so the way that you're going to calculate and propagate error when it's an absolute uncertainty problem is you're going to calculate your measurement by just adding or subtracting. So in the instance of perimeter, take all of those length measurements and add them all up. Then you're going to add up all the absolute uncertainties associated with each of those length measurements, for example, and then you'll take whatever that final answer is that you got in step 1 and put the plus or minus sign, and then have what the sum of your absolute uncertainties is from step 2. Okay? So I cannot mention this enough. The way that you tell if it's absolute uncertainty is that the units do not change. So if you start with one unit and you can convert at the end to get the same unit, that means your units are not changing. Okay? An example would be, say you have a jug of water with an unknown amount of water, and you have two beakers. You have a 500 milliliter beaker with increments every 50 milliliters and a 100 milliliter beaker with increments every 20 milliliters. So you fill up the 500 milliliter beaker 3 times and you fill up the 100 milliliter beaker 4 times. Okay, so step 1 is figuring out what your measurement is by adding or subtracting. So in this case, we're going to be adding, right? So how much water is in the jug? Well, that's going to be 3 times 500 and 4 times 100, right? So 3 times 500 is 1500, 4 times 100 is 400, so that gives us a total of 1900 milliliters. The next thing that we're going to do is we're going to find the absolute uncertainty of the water in the jug, and we're going to do this by adding the absolute uncertainties. This, of course, means that we need to find the absolute uncertainties first, okay? So you can see I already have the absolute uncertainty for our larger beaker, right? Because there are increments every 50 mils, so 1/2 times 50, that gives us 25 mils. Then for our smaller 100 milliliter beaker, there are increments every 20 mils, so half of 20 is 10. We filled that up 4 times, so 3 times 25, that's 75. 4 times 10, that's 40. When you add those together, you get 115 milliliters. So how can I tell that it's a simple addition/subtraction problem? everything is in milliliters. Even if I chose for some godforsaken reason to convert how much water is in the jug to 1.9 liters, I could still convert it back to milliliters. No sweat. Okay? So at the end of the day, what you're left with is, if you want to write it in standard form, so measurement uncertainty format, that would be 1900 plus or minus 115 milliliters. Now we're going to discuss how we would propagate error using relative uncertainty. Okay? Now this is going to be for those problems where there's multiplication or division of multiple measurements. So say you have meters and meters and you go to meters squared for an area. Say you have meters, 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 and you go to a volume, so you go to meters cubed. Say you have density, so you have completely different units. You have grams and you have milliliters, and you go to grams per mil, etc. The list goes on and on. Okay? The way that you would propagate your error using relative uncertainty is, first you would calculate your final answer ignoring your uncertainties. Okay? So if they ask you for the area of a rectangle or something, then you would multiply the length times the width. You wouldn't worry about what the uncertainties associated with the length and the width were. You would just calculate it. Okay? The next thing that you would do is you would calculate the relative uncertainties for each measurement. So you would take your uncertainty associated with your length, divide it by the measurement of the length, then take your relative uncertainty for your width, divide it by the measurement for the width. You would add both of those quantities together, okay? And then once you have that sum of your relative uncertainties for your length and your width, you would multiply that by your final answer, okay? And I know that was like a lot of words, and the best way to understand this is just to work through a problem. So that's what I'm going to do. Okay, so here's the example. Say we have T-Rex over here, and he's trying to paint his house, but he can't reach certain places, right? He's got little arms, right? So unfortunately, he's only able to finish this swath of paint here. And I'm going to tell you that he lives in a square house that is 21 meters plus or minus a half a meter. Okay, so that means this is 21 by 21. Okay, and his completed swath is 6 meters plus or minus a half a meter. Okay, so this is 6 meters wide. Okay, so we want to figure out what area he has painted on one wall. The reason for that is, say that he needs to hire Mr. Velociraptor, who's going to finish the job, and so he needs to let him know what area he's already painted so that Mr. Velociraptor can give him an estimate on what is currently unpainted. Okay? So just to check to make sure that you understood how we find absolute uncertainty, what did T-Rex use to measure his house? Meaning, we can see that the absolute uncertainty is a half a meter for both of these measurements, so what did he use? T-Rex used a meter stick, right? Because meter stick is an analog device, so if there are no markings on this meter stick, then 1/2 times a meter is a half a meter, so he used a meter stick. Okay, so the first step in finding our relative uncertainty and propagating error is we want to calculate the final answer without any uncertainties, okay? So just the area of paint that T-Rex has completed on one wall, okay? So the swath is 6 meters wide. We know the wall is 21 meters long, so 6 times 21, that gives us 126 meters squared. All right, so now we can move on to step 2, and I'll be honest, most of the time I combine step 2 and step 3 together, but just for the first time that we're working through this, I want to make sure that everybody can follow, so I didn't want to combine any steps. All right, so first thing we're going to find is we're going to find the relative uncertainty for the height of the swath, okay? So we know that he painted a 6 meter plus or minus a half a meter wide swath, okay? So the height of the swath is 6 meters, okay? So 0.5 divided by 6 gives us 0.08. Meters cancel with meters, right? So now this is unitless. Then for the width or length of the wall, however you want to think about it, so this length here When he measured it, it was 21 meters plus or minus a half a meter. So 0.5 uncertainty divided by measurement 21 meters, we get 0.02. Again, unitless because both meters cancel with meters. So now we move on to step 3, which, as I mentioned, I usually combine with step 2. We're going to add our relative uncertainties. So we take our 0.08, we add it to our 0.02, and we get that the sum of our relative uncertainties is 0.1. Now the last step is to get everything in the same unit. So we're going to multiply the sum of the relative uncertainties, which was our 0.1, by our final answer, which is 126 meters squared, and this will give us our absolute uncertainty of whatever we're measuring, in this case area, right? So we have 126 meters squared times 0.1, that gives us 12.6 meters squared, or more simply, with correct number of sig figs, that is 13 meters squared. So I know up here I didn't say to write your answer in standard form, but that's what we're going to do. So what area has he painted on one wall? He's painted 126 plus or minus 13 meters squared. So that's the number that he would want to give to Velociraptor for his estimate. Although in reality, as you'll see on the next slide, he would probably want to do some absolute uncertainty error propagation to give Mr. Velociraptor the area that he's painted on all 4 walls. But we'll get to that in a minute. The last thing that I want to mention is how we can tell that this is a multiplication or division problem. The way we can tell is because the units change, right? We started out with 2 separate meters measurements, and then we ended up with meters squared, right? So you can see here in the answer, we start out with meters, we end with meters squared. And you cannot convert back to that by multiplying by a multiple of 10. So yes, our units have changed. That means we had to use relative uncertainty. We could have used percent uncertainty as well. But we'll get to that at a later slide. Now, as I mentioned before on the previous slide, what T-Rex probably wants to provide to Mr. Velociraptor is how much he's painted on all 4 walls. That way, Mr. Velociraptor knows how much he needs to paint on all 4 walls, right? Because T-Rex isn't looking to just paint one of his walls, which is what the estimate on the previous slide gave us. He wants to paint all 4 walls, right? And so we're actually going to be using absolute uncertainty and propagating the error that way, because we're going to start with meters squared and we're going to finish with meters squared. So as I mentioned, this is an absolute uncertainty error propagation problem. So if we want to know what area he painted on all 4 walls, well, we know on one wall he had 126 plus or minus 13 meters squared. So that means on 4 walls, we need to multiply both quantities by 4. So 4 times 126 gives us 504. 4 times 13 gives us 52. So when he goes to Mr. Velociraptor, he's going to say, hey, I already painted 504 plus or minus 52 meters squared. I need you to paint the rest. Can you please give me an estimate of how much that will cost? Last but not least, we're going to discuss percent uncertainty. So the way that you calculate percent uncertainty is you take the relative uncertainty and you multiply it by 100. Okay, so recall that relative uncertainty is just your absolute uncertainty divided by your measurement. So another way you could write this is absolute uncertainty divided by your measurement times 100. But that would be how you would find percent uncertainty. So let's say, for example, we want to find the percent uncertainty of a narwhal that has a length of 6.4 meters if the absolute uncertainty of said narwhal is 6.2 centimeters, aka 0.062 meters, okay? Because remember, we want to, just like with the relative uncertainty, we want to make sure everything is in the same unit, okay? So if we were to write this in standard form, that would mean we have our measurement of our narwhal, the length of which is 6.4 meters, plus or minus 0.062 meters, which is the absolute uncertainty of our measuring device. Yes, I realize that this is a real weird ruler, okay? And you're going to encounter that in a lot of these problems. There are going to be rulers with increments that you've never seen before. Yes, I know. I've never seen a measuring device that has lines every 12.4 centimeters, okay? But try to put that out of your mind when you're doing these problems, okay? So if we wanted to calculate the percent uncertainty, we know that the percent uncertainty is the relative uncertainty times 100, or the absolute uncertainty divided by the measurement times 100. So our absolute uncertainty is 0.062 meters divided by our measurement, that's 6.4 meters. We multiply that by 100, and we get that the percent uncertainty is 0.97%. All right, so just in case you fell asleep on some of the other slides, this is a summary of all the uncertainties that we just covered. So absolute uncertainty, and keep in mind this is specifically for analog only. For digital, you don't need to do a calculation, is simply the smallest increment of that measuring device. But for absolute uncertainty, for an analog device, that's going to be 1/2 times the smallest increment on your measuring device. Then for relative uncertainty, that's going to be your absolute uncertainty divided by your measurement. And then for percent uncertainty, that's going to be your relative uncertainty times 100. So this is a review of how we're going to propagate our uncertainty/error and some rules of thumb. Okay? So as you'll remember, absolute uncertainty is when all of your measurements and their associated uncertainties have the same unit. Okay, keep in mind if you can multiply by an order of magnitude to get the same unit, this still counts as the same unit. Okay, so if you have a couple of volumes and one of them is in milliliters and one of them is in liters, you can convert all of them to liters or all of them to milliliters, so that means all of your measurements are in the same unit. Okay. Now, for relative uncertainty and percent uncertainty, you're going to want to use these if your measurements and their associated uncertainties do not have the same units. Okay? Relative uncertainty is a little bit more common than percent uncertainty, but you can use either one if your units are different. Okay? With percent uncertainty, it's a little bit more handy if you don't have the same units, of course, but if the uncertainty is very small relative to the measurement and there are a few significant figures, okay? Because best practice dictates that we keep the correct number of decimal places as dictated by sig figs, okay? So that's when percent uncertainty might be a little bit more handy, and you're going to notice in the lab that this is exactly what we do use. We use percent uncertainty, and it's for this reason, okay? So the previous slide had a lot of words on it, and just to make sure that the concepts were understood, I came up with 3 different scenarios, and I want you to decide which uncertainty you should use for each scenario. Okay, remember the 3 uncertainties are absolute uncertainty, relative uncertainty, and percent uncertainty. So I'd recommend pausing the video at this point, read through each scenario, and come up with which uncertainty you think would be best in that situation, and then unpause and see what I came up with. So the first scenario says the mass of a wooden block is 600 plus or minus 0.1 grams. The volume of the block is 1,000 plus or minus 5 milliliters. What is the density? Okay? So what I want to know is which uncertainty should I use in this instance? So for the first scenario, I would choose percent uncertainty, but relative uncertainty would also work. The reason that I choose percent uncertainty over relative uncertainty is because there is a huge difference between our measurement and our uncertainty. And so by using percent uncertainty, we'll be able to see a little bit more of that precision in our uncertainty without violating any significant digits rules. Moving on to the second one, the length of a table is 4 plus or minus 0.01 meters, and the width is 3 plus or minus 0.01 meters. What is the area? So in this scenario, what would I prefer to use? Which uncertainty method? Absolute, percent, or relative? So in this example, I would use relative uncertainty over percent uncertainty, but both would work. The reason that I would use relative uncertainty is because it's a simpler calculation. There's no additional step where you're multiplying by 100 for percent uncertainty. And in this case, our measurement and our uncertainty are not so different, and so we don't really have to worry about losing the precision of our uncertainty because there's that huge difference between the measurement and the uncertainty. Last but not least, a ruler measuring millimeters is used to find the perimeter of a rectangular tile. The longer sides of the tile measure 625 millimeters, and the shorter sides measure 42.5 centimeters. What is the perimeter of the tile? So in this instance, there's only one option, and that's absolute uncertainty. Your units aren't changing. Yes, I did do a little sneaky thing here where I have one of the dimensions in millimeters and one of them in centimeters. But remember, if you can use some order of magnitude and change it to the same unit, which you can, in this case, centimeters and millimeters, just being separated by an order of 10, then this is absolute uncertainty, okay? And in this case, our units aren't changing, so there's no reason to use percent uncertainty or relative uncertainty. They would only muddy the waters. You want to use absolute uncertainty.
So now that we've gone through which uncertainty was the most appropriate uncertainty in each scenario, I've taken the liberty of giving you what the answers would be to each of these problems for any of the appropriate answers. So feel free to look through these and practice them on your own. Make sure that your answers match these answers. If they don't, feel free to come to me or whoever your lab instructor is with questions.
If you found this exercise a little bit confusing, take comfort in the fact that the more that you do this, the easier this stuff will get, and also that you can use relative and percent uncertainty interchangeably, and nobody will really give you a hard time about it unless one was specifically requested over the other. So let's switch gears a little bit. We're going to talk about average, standard deviation, and range. These are all topics that are going to be covered in the pre-lab as well. So the first thing that I'm going to discuss is average, or X bar. Okay, so if you've taken a statistics class before, this notation down here probably looks really familiar to you, but if you haven't taken it before, you might be a little confused by it. And so I just wanted to take a minute and break it down for you. Okay, so this right here, this sigma, that means the sum. Okay, so anything to the right of your sigma is going to mean you're adding that quantity up. So X subscript I, that means I'm adding this quantity up. Okay? Now, above the sigma, I have an N. Okay? Now, N is telling me how many numbers I have in the series. Okay? And then I, so you can see that this is X subscript I is telling me which number to start with in the series. Okay? Then when all of that is said and done, when I've summed up xi, starting with the first number and going all the way to the last number, then I'm going to multiply that by 1 over n. Okay? So you can see over here, if we expand that, that means we have 1 over n plus x1 plus x2 plus x3, and then whatever numbers are in between, all the way out to our last number, xn. Okay? Yes, I am aware that this is a really complicated way to illustrate a very simple concept, but this is how mathematicians do. So now we're going to go over a quick example of how you would calculate average. So say Hagrid measures the lengths of 6 unicorn horns. The lengths in centimeters are as follows: 26.1, 22.3, 24.5, 20.9, 25.2, and 27. What is the average length of horn for these 6 unicorns? So you add up all of the lengths, you divide by however many numbers there are in the series, which there are 6 measurements. Okay, so when you sum up all these numbers, you get 146. You're going to divide that by 6. The average ends up being 24.3 centimeters. And hopefully, like Hagrid is saying over here, you haven't eaten that, because you should not have, because as you know from Voldemort, he lived a half-life or a cursed life after drinking unicorn blood. Moving on. So this takes us to standard deviation. Standard deviation is going to represent variation or uncertainty in a series of numbers. Now, in this class, you should only be using sample standard deviation. Population standard deviation is for your biology classes, okay? Population standard deviation means that right here, if you see this little mu guy, you have the population mean. That means you have literally taken millions of measurements. Okay? So you are certain about what that mean is. Okay? Thankfully, or maybe not thankfully, we are not taking millions of measurements in physics class. Therefore, we are going to be using sampled standard deviation, which means we are going to compare each number in our series to the average of all the numbers in our series. Okay? So just like before, I'm going to break down what this whole mess means here. You can see once again we have the sigma, and once again below it we have I is equal to 1. That means that we're going to start with the first number in the series, and we have n above it, which is telling us to continue on until we get to the last number in our series. Okay? To the right of the sigma, so remember, sigma means that you're going to be adding up the quantities that are to the right of it. So to the right of the sigma, we have a number in our series minus the average of all the numbers in our series. And then once we find that difference, we are going to square that quantity and then add it to the next number in our series minus the average squared. Okay? In the denominator, we have n minus 1, so let's just say that we have 10 numbers, okay? So that would mean n would be 10, we would subtract 1, so we would have 9 in the denominator, okay? So after you do everything in the numerator, that means simplifying what's in the parentheses as well after you've added everything up. Then you would divide by n minus 1. The very last step in sample standard deviation calculation is taking the square root, okay? So I know that's a lot of words. I think the best way to really illustrate it is to show you an example. So an example would be Hagrid measures the lengths of 6 unicorn horns. The lengths in centimeters are as follows, so same numbers we had before. What is the standard deviation / how much variation is there in unicorn horn length? Okay, so we're going to calculate what is the standard deviation. So the first thing that we're going to do is we're going to figure out what we have to the right of our sigma, and we're going to add those quantities together. So as I mentioned, we're going to take each number in our series and subtract the average, and then we're going to square that difference. So the first number in the series is 26.1. We're going to subtract the average, which we calculated a few slides ago, which was 24.3. And then we're going to be squaring that quantity and then adding it to the next number in the series minus the average squared. Okay? So you do that for each number in the series. Okay? And then since we have 6 numbers in the series, right, n is equal to 6, so we have 6 minus 1 in the denominator. And then at the end of all of this, we're going to be taking the square root. Okay, so remember, please excuse my dear Aunt Sally, right? So we want to do what's in the parentheses first, so we find what the difference is between each of those values, right? Then we move on to the excuse part, right, which is our exponent. So after we find what's in the parentheses, we're going to square each of our numbers. So that's what we've done here. All of these numbers have been squared. Then we're going to add up all of the numbers in the numerator. Okay, so then we end up with 26.94, and we're going to divide by our denominator, which is 5. Remember, 6 minus 1, that gives us 5. So we do that, we get 5.4. The very last thing that we want to do is we want to take the square root. So the square root of 5.4 is 2.3 centimeters. And so if we want to figure out how we would express the standard deviation / uncertainty in standard form, this is how you would do that, right? You would take your average plus or minus your sample standard deviation. Okay, so 24.3 was our average, plus or minus, we just calculated our sample standard deviation, that's 2.3, and the unit is centimeters. Sorry to harp on this again, but I cannot say this enough. Do not use population standard deviation in this class. That means, since we're going to be using Excel a lot, never use the Excel function stdev.p, because that is the population standard deviation. There's a regular just STDEV, and there's an STDEV.S. Those are totally cool. Just don't use this one. Why? Because this implies that when Hagrid collected these 6 unicorn horns, these were literally the only 6 unicorns in existence to ever have been in existence, okay? And that is not what we're going to be measuring in physics. We are not doing nearly enough measurements to say anything about the population, okay? So please, please, please do not use population standard deviation in this physics class. Now, I know I just harped on how important it is that you do not calculate population standard deviation in this class, but if you were curious about how it would be calculated, say that you don't have a good example in a biology class or something, this right here is how you would calculate the population standard deviation. And of course, you can see here, one of the pitfalls of using population standard deviation when you shouldn't is that you are going to underestimate what your uncertainty is. And that's because we know about the entire population, in which there are just 6 of them, not 6 minus 1, and so that's why we end up with a smaller number overall. But as I mentioned before, we will not know the entire population of any of the measurements that we're collecting because we just don't have time to collect nearly enough measurements to represent a population mean. So please do not use population standard deviation in this physics class. Okay, so now let's discuss range. So what range is it's your average value plus your sample standard deviation and your average value minus your standard deviation. This gives you your maximum value and your minimum value respectively. So let's say, for example, Dumbledore has a 30-centimeter standard owl post box to ship a unicorn horn. So he asks Hagrid if the box will be large enough. What is the range of unicorn horn lengths? Is the box large enough? Okay, so we know that the average length was 24.3, so that's our average here. And we know that our sample standard deviation was 2.3 centimeters, right? So that's the S here. So we're going to add our sample standard deviation and subtract our sample standard deviation to find our range. So when we subtract, we get 22 centimeters. When we add, we get 26.6. Now, this is the upper limit, so this is what we're really concerned about. And yes, the box is large enough because the 30-centimeter box is bigger than our maximum value for our range, which is 26.6. So Dumbledore should be good to go. So another topic that I want to go over to make sure that everybody's on the same page is percent error versus percent difference. Percent error or percent uncertainty, that's going to be comparing an experimental value that you get in the lab to a known or theoretical value. So an example of a known or theoretical value would be 9.81 meters per second squared for gravity, or the density of water, 1,000 kilograms per meters cubed. Those are theoretical values, okay? Many scientists over many, many years have done the same experiments over and over again and gotten the same result, which has given us the theoretical value, or nearly the same result. And so our theoretical value is the average of all of those very careful measurements. Okay? So percent error is going to be comparing that theoretical value that many scientists have confirmed with your experimental value that you got in the lab. Okay? So the way you calculate it is you take the absolute value of your theoretical value minus your experimental value, you divide by the theoretical value, then multiply by 100. And you can see by looking at this that this essentially tells you how close you were to that theoretical value. And that's exactly what the purpose of percent error or percent uncertainty is. So percent difference compares to experimental values. So you might be asking yourself, what is an experimental value? So an experimental value would mean that you're finding the same quantity, but you're using 2 different experimental methodologies to do so. A great example of this is in Lab 8. You're going to be given a metal sphere, and you're going to be asked to calculate the volume of it using 2 different methods. So the first method that you're going to use is you're going to take a pair of calipers, and you're going to figure out what the diameter of the sphere is, and then in turn calculate the radius from the diameter, plug it into 4/3 pi r cubed, and figure out the volume. The other way that you're going to figure out the volume of the sphere is you're going to take it and you're going to submerge it in water, and you're going to see how much water is displaced by the metal sphere. Okay, so both of these methods tell you what the volume of the sphere is, but neither one of these methods would be the volume that's reported by the company, right? If you had the volume reported by the company, that would be your theoretical value, and if you were comparing your experimental value to it, you would use percent error. In this case, you're using two experimental methodologies, and neither one you really want to weight more than the other, because neither one is the theoretical answer, right? And so that you would use percent difference in this instance. So the way to calculate percent difference is you would take the absolute value of experimental value 1 minus experimental value 2, divide it by the average of experimental value 1 and experimental value 2, right? Because we don't want to weight one over the other. We're weighting both of them equally because they're both experimental values. And then you would multiply that fraction by 100 to get the percent difference. So now to tie together several of the concepts that we were just discussing, I want to talk about accuracy versus precision in terms of percent error, range, and standard deviation. So on this slide, you can see a pretty common illustration of precision versus accuracy. So on the first dartboard here, we see a really high precision but low accuracy example. So what that means is that we're going to have a small standard deviation, right? Because standard deviation measures our variation between our measurements. So there isn't a lot of variation between them. They're all very close together. It's also going to have a small range because they're clustered close together, so there isn't a big spread of these values. But it is going to have a very large percent error because the percent error is comparing how close these values are to the bullseye, right? That's our theoretical value, is the bullseye. Now here, in the second example, we have low precision, but we have high accuracy. So there's a pretty big spread of these arrows, right? And they're all pretty close to the bullseye. So that means that we're going to have a large standard deviation and large range, right, because there's a large spread. But we're going to have a small percent error because all of these values, although they're not close to one another, they are very close to the bullseye. Now, if everything goes to hell in a handbasket, which is exactly what we don't want in the lab, we have low precision and low accuracy. So we've got a huge spread. None of these are close to the bullseye. So that means we have a large standard deviation, large range, and large percent error. Now, ideally, what we want to do is we want to have high precision and high accuracy, okay? So that means we want all of our measurements to be nice and close together, and we want them to be very close to the bullseye. This will mean that we have a small standard deviation and small range because they're close together, and then we will have a small percent error because they're very close to the bullseye. Now that pretty much summarizes all the review material, so we're going to get into the pre-lab practice problems now. So you can see on the right-hand side here, these are all the pre-lab practice problems that I'm going to be going over. Now, the 7 of them that are listed here, there are going to be problems that are very similar to those on quiz 1, so it does behoove you to do this exercise and really understand it in order to do well in the quiz. So if you haven't already done so, I'd recommend that you pause the video now, work your way through all of these problems on your own, and then play the video and see me work through the problems. If you have already worked through the problems, though, I am going to continue on and start with the first problem. So pre-lab practice problem number 1 says the instantaneous speed of a car measured from the speedometer reading every second for 10 seconds in units of miles per hour are 0, 1, 9, 11, 17, 10, 28, 40, 36, and 55. The average of the above readings in miles per hour is about blank. Okay, so we want to recall our formula for calculating average. Okay, so what we're going to do is we're going to take all of our values that they gave us. We're going to add them up in the numerator, then divide them by the number of values there are in the denominator. So we do that, we get 207 divided by 10. This simplifies to 20.7 or 21 miles per hour when we think about significant figures, right? None of these values up here have a decimal point, therefore our answer, which is the average, shouldn't have a decimal point either. So Prelab practice problem number 2 uses the same data from the speedometer as the previous problem, but this time we're going to be finding the sample standard deviation. Okay, so as you'll recall from earlier slides, the sample standard deviation can be calculated using this formula. And it is a bit of a doozy if you're calculating it longhand, as I have. You are more than welcome to use a graphing calculator, however. But if you are calculating it longhand, this is how you would do it. So remember, you're going to be adding up everything that's to the right of the sigma, right? So starting with the first number in the series, you're going to subtract your average value, right? And then you're going to square that, add it to the next one, right? So the first number in the series is 0. Our average, which we calculated on the previous slide, is 21. So 0 minus 21. We're going to square that quantity, add it to the second number in the series, which is 1 minus 21, square that, so on and so forth until we get to the last value in the series, which is 55. Subtract the average, square it. In the denominator, we have n minus 1. Well, we have 10 numbers, so it's 10 minus 1. And then the last thing we're going to be doing is taking the square root, right? So from please excuse my dear Aunt Sally, the first thing that we want to do is the math inside the parentheses, right? So that's what I've done here. We've computed what the difference is within the parentheses for each of these values. The next thing that we want to do is we want to move on from please to excuse, so the exponent. So we're going to square each of these quantities. So that's what these values are here. We've squared all the quantities, and you can see there are negative numbers, but you know that a negative times a negative is a positive, so we lose all those negative signs once we've squared the terms, right? And you'll notice that I just simplified our denominator. 10 minus 1 becomes 9. Now we want to add up all of these guys in the numerator, so that gives us 3,013. Then we want to divide by our denominator, so 3,013 divided by 9 gives us 3.347 repeating. Then we want to take the square root. The square root is 18.3, but as we discussed on the previous slide, there are no decimal points, so we want to keep it with the correct number of sig figs, which means not having anything in the tenths place, since we don't know that kind of precision from the speedometer. So we round it off to 18 miles per hour. That is the sample standard deviation of the above readings. Prelab practice problem number 3 says the mass of a ball is measured as 60.2 plus or minus 0.5 grams. What is the same measurement given as percent uncertainty? So recall, percent uncertainty is 100 times relative uncertainty, or it is our absolute uncertainty divided by our measurement times 100, right? Because relative uncertainty is this fraction right here. Okay, so 60.2 grams, that's our measurement, right? That's this guy here. 0.5 grams, that's our absolute uncertainty. That's this guy here. So to find percent uncertainty, we're going to multiply that fraction by 100. So absolute uncertainty divided by the measurement, or 0.5 grams divided by 60.2 grams. So when we multiply out, we end up getting that this is equal to 0.83%. Now, just like before, if we round to the correct number of significant figures, the answer would be 60.2 plus or minus 0.8%, because of course we don't really want to go past the tenths place, since we can tell from our measuring device that our measuring device didn't go past the tenths place. Prelab practice problem number 4, how many significant figures does the measured value of the mass of the ball have? So this is just a little recap of what the rules of significant figures are. We know that all non-zero digits are always significant, and we know that any zeros between two significant digits are significant. So these, rule 1 and rule 2, are the important rules that apply here. So we know from rules 1 and 2 that 60.2 has 3 significant digits. So the only thing you might have been questioning is whether or not the 0 is significant, and Rule 2 tells us that indeed it is significant, which gives us our 3 significant digits. One thing that I did want to mention is that Rule 4 talks about our placeholding zeros. So placeholding zeros aren't significant. They're zeros that are going to disappear when the number is put into scientific notation. Okay, so that's a really good test. If you're not sure about whether or not a zero is significant or not, put it in scientific notation. If that zero goes away, then it's not significant. All right, pre-lab practice problem number 5. A mass of a box is described as 52 plus or minus 0.5 kilograms. What is the range of values in kilograms in which you expect to find the mass of the box? So let's recall that the range is our average value plus the sample standard deviation and the average minus the sample standard deviation, right? Adding the sample standard deviation gives us our maximum value. Subtracting the sample standard deviation gives us our minimum value. Okay, so we're going to do just that right there so that we can compute our range. So 52 plus a half, that gives us 52.5. 52 minus a half, that gives us 51.5. That means the range of values in which we expect to find the box is going to be between 51.5 to 52.5. Pre-lab practice problem number 6. The volume of milk in a jug is determined by pouring it out into a container, first using a 50 milliliter jar in which a 0.5 milliliter error in measurement is estimated, and then using a smaller 5 milliliter flask in which a 0.25 milliliter error in measurement is estimated. The milk was poured out 5 times using the 50 milliliter jar and 8 times using the 5 milliliter flask. What is the measured volume of milk in the jug in milliliters? State the answer in standard form, so that would be your total volume plus or minus the estimated uncertainty in volume. Okay, now recall that with absolute uncertainty error propagation, our units aren't changing, right? So everything here is in milliliters. That means our units aren't changing. Our final answer is going to be in milliliters, and all of the values that we were given are also in milliliters. Okay, so that means we can directly propagate the errors just by adding them up, right? Just like we do with the actual volumes themselves. So we know with the bigger 50 milliliter jar, that was poured out 5 times. So we're going to multiply 5 times 50 and 5 times 0.5. So that gives us 250 plus or minus 2.5 milliliters. Then for the smaller 5 milliliter flask, we poured that out 8 times, right? So 8 times 5 is 40, 8 times 0.25 is 2. So that's 40 plus or minus 2 milliliters. Then we're going to add these up, so both the volumes and the estimated uncertainties. Okay, so 250 plus 40, that gives us 290. 2.5 plus 2 gives us 4.5. So our final answer is 290 plus or minus 4.5 milliliters, or you could express that as 290 plus or minus 5 milliliters, because it is a very common practice to round off your uncertainty to one significant digit, which would be 5 milliliters. Okay, so feel free to do that as well. And in case you're concerned, there will never ever be 2 multiple choices, one of which is 290 plus or minus 4.5 milliliters, and the other of which is 290 plus or minus 5 milliliters. That will never ever happen, so you don't have to worry that if you simplify it one way or the other, you'll get the wrong answer. That will not happen. All right, pre-lab practice problem number 7. The dimensions of a table are measured with a meter stick. The length of the table is measured as 3.431 meters, and the width of the table is measured as 2.187 meters. The uncertainty of each of these measurements is 2 millimeters. What is the area of the table in meters squared and its uncertainty? So in this case, we know that we're going to need to either use relative uncertainty or percent uncertainty. That's because we're going to have an area that's in meters squared at the end, but we're starting out with a width and a length that are in just meters. So we do have a unit change that's taking place. So speaking of unit changes, the very first thing that I'm going to want to do is I'm going to want to make sure that all of my information is in the same unit. Now you may be wondering to yourself, which unit do I choose? Should I use meters or should I use millimeters? My recommendation is going to be take a look at what all of your multiple choice answers are in. Are they in meters or are they in millimeters? If they're all in meters, then you should convert everything to meters. If everything is in millimeters, you should convert everything to millimeters. Okay? In this case, we can see that the answer is going to be in meters, and so I'm going to convert everything to meters. So that gives us the length is 3.431 plus or minus our uncertainty, which is 0.002 meters. Then our width is 2.187 plus or minus 0.002 meters. So now we move on to the first step, which is to calculate the final answer without any uncertainties. So this is a rectangular table. That means to find the area, we need to multiply the length times the width. So that's just 3.431 meters times 2.187 meters, and that gives us 7.504 meters squared. Okay, so we're just going to file that away for later. As I mentioned earlier, I'm going to combine steps 2 and 3 since it saves me some space. So that means we're going to calculate the relative uncertainties for each measurement, and then we're going to add the relative uncertainties. Okay? Remember, this was step 2, this was step 3. All I've done is combine 2 and 3 together. Okay? So to get the relative uncertainties, we're going to take our absolute uncertainty and divide it by our measurement for both of our measurements, right? So 0.002 divided by 3.431, 0.002 divided by 2.187. That gives us the decimal values 0.000583 and 0.000914. Then for step 3, when we add both of those together, we get 0.001497. Then for our last step, we're going to multiply the sum of the relative uncertainties, which is this quantity here, the 0.001497, by the final answer that we got in step 1. Okay? So when we multiply those together, since we want to make sure that we're getting that same unit, which in this case is meters squared for area, we get 0.011 meters squared. Okay, then if we want to express it in our measurement uncertainty format, that would be 7.504 plus or minus 0.011 meters squared. And then remember, it's always acceptable and it's a common practice to round off your uncertainty to one significant digit. So reporting your answer as 7.50 plus or minus 0.01 meters would also be correct. Okay, either one, both of them are equally correct. Neither one is better than the other. Okay. So that pretty much wraps up the pre-lab practice problems. I have one more slide, which is just sort of a summary of what you can expect on quiz 1. And so let's go over that now. So you'll have 30 minutes to complete quiz 1. There are going to be 10 multiple choice questions. 7 of the problems are going to be similar to the pre-lab practice problems we just covered. 3 of the problems are going to be review. And when I say review, I mean they're going to be from the math diagnostic test. If you have not taken the math diagnostic test, it is highly recommended that you do so and score yourself. And score yourself honestly, too. All right? A score lower than 70% on the math diagnostic test strongly suggests that there are math courses you need to take before you will be successful in Physics 1. If you do not have a really strong background in trigonometry and algebra, you are really going to struggle to keep up in Physics 1. And I would highly recommend that you take those classes before you try to attempt Physics 1. Okay? That being said, future quizzes will be a little bit different than quiz 1. So quizzes 2 through 12, those are going to have 5 multiple choice questions about the current topic and 5 multiple choice questions about the previous topic. Okay, so for example, quiz 4 will have 5 questions about projectile motion, that's topic 4, and then 5 questions about free fall, which is topic 3. Hopefully you found this information useful, and best of luck on the quiz.